All right, let's start. Welcome, everyone. Welcome back after a short summer break. Welcome back to the third colloquium in the series of IPN colloquia. And to remind you all, we are organizing these colloquia because we are celebrating the 25th anniversary of IPN this year. And for now, it gives me enormous pleasure to announce the speaker of today, which is Edward Lee. Edward Lee is a professor of the Graduate School and Distinguished Professor Emeritus in Electrical Engineering and Computer Sciences at the University of California at Berkeley. He's also co-founder of two companies, Kronos Incorporated and BDTI Incorporated. Professor Lee's research studies cyber-physical systems, which is integrating physical dynamics with software and networks. His focus is on the use of deterministic models as a central part of the engineering toolkit for such systems. He's also a director of iSci-Fi, which is the Berkeley Industrial Cyber-Physical Systems Research Center. But he's also very famous, I must say, for his hugely inspiring talks on the philosophy of technology. And hopefully we'll see a little bit from that today. Professor Lee is a fellow of IEEE. He was a NSF Presidential Young Investigator and has received numerous other awards. Just to name a few of those, the 2016 Outstanding Technical Achievement and Leadership Award from IEEE Technical Committee on Real-Time Systems, the 2019 IEEE Technical Committee on Cyber-Physical Systems Technical Achievement Award, the 2022 European Design and Automation Association Achievement Award, and the 2022 ACM SIGBET Technical Achievement Award. Well, in today's colloquium, Professor Lee will talk about certainty or intelligence. Pick one of those. And I'm very much looking forward to that talk. But before we start, let me first do one practical announcement. So if you have a very short, urgent question during the talk, please raise your virtual hand and you will be allowed to ask your question by voice using your microphone. And of course, after the talk, we will allow everyone to ask questions in the same fashion. Now, without further ado, I would like to give the floor to our speaker of today. Edward, please go ahead.
Thank you, Andy. I really appreciate the invitation. This is one of my favorite topics these days. And hopefully I will be able to share some of my enthusiasm. So let me make sure to share the appropriate screen here. Okay, so hopefully you can see my title slide now, yes?
Yes, we can see it, yes.
Good, okay. So what's the problem that I'm addressing here? Well, the work that I do, the work that I've been doing for the last 40 years in my career is all oriented around cyber-physical systems, systems that involve computation and physical processes, and these are often safety critical systems, automotive systems, for example, aircraft control systems, things like that. And the tradition that has been kind of a guiding principle throughout my career is that the software for these systems needs to be very heavily vetted, much more heavily vetted than many general purpose software systems. And so we really want to be able to prove things about them. There's a lot of application of formal methods in this context, and you want to be really quite sure of the behavior of this software. So the problem that we're having right now is that there's kind of a AI revolution that I think everyone here is well aware of, that has made it very clear that you're really limiting yourself if you don't include these kinds of technologies in systems. And pretty much, I think all system designs are in the process of integrating AI into them. And the dilemma that we face here is that if we're designing autonomous systems, we want certainty. We want proofs that only safe behavior is possible. But we also want intelligence and especially adaptability to circumstances not previously seen. I mean, I think this is one of the key limitations that this technology addresses, is its ability to generalize beyond what the designers anticipated. My claim in this talk is that these are actually fundamentally conflicting goals. And I'm going to give you a couple of different arguments for this. And the first argument is kind of technical, and I apologize, but it'll involve a little bit of math, right? But the second argument is really much more foundational and much more philosophical. Now, I should point out that many of the images that I am showing here are generated by ChatGPT, and in particular, the image that you're seeing right here was prompted by exactly the text that's on this slide, and I think it's a pretty interesting rendition of that text. So, all right, so we're going to start first with a fairly technical argument, and in order to set the stage here, I have to explain that when it comes to probability theory, there's kind of two camps of thinking: the Bayesians and the frequentists, and mostly they agree on the mathematical toolkits that they use, but they disagree on the meaning of probability. And I'm a Bayesian, and everything that I present here is going to be from the perspective of a Bayesian, where a probability is not a measure of underlying randomness, but rather a measure of uncertainty. It's a measure of lack of knowledge, and not in particular. I mean, a Bayesian is perfectly comfortable applying probability theory to a fully deterministic system, because you can't know everything about the system. Therefore, probability is a reasonable way to model your uncertainty, your lack of knowledge about the system. A frequentist would be less comfortable applying probability to a deterministic system, because the frequentist would expect the behavior to just always repeat exactly the same behavior. So from the perspective of a Bayesian, the core tool used by a Bayesian is Bayes' law. Bayes' law is also used by frequentists in probability theory, but the meaning of the law is a little bit different. Okay, so let's take a look at Bayes' law. So let's suppose that S is a statement about which you want to be certain. So you're designing an automotive controller, and you want to prove that the car will stay in the lane. And let O be some experimental observation of behavior. You've got the car on the road, you make a measurement, and the car followed a certain trajectory, and that trajectory is represented by O. So Bayes' law gives us a way to relate 4 different probability measures that are relevant to these two statements. So let me walk you through these, okay? The first probability measure is a prior probability. So this is the probability that the car stays in the lane with no other conditioning, okay? This is again, from a Bayesian perspective, this is a subjective judgment. So you have some design, you think, oh my God, I don't really know for sure whether this is, the car is going to stay in the lane. So I give it a prior probability measure that is some broad measure that allows for the car to not stay in the lane, okay, for example. But it's subjective. Then you have the probability if your S is true, in other words, the car does stay in the lane, then you have a probability measure for what your measurements are going to reveal. Okay, so there's a certain probability that the car will follow a certain trajectory given that it stayed in the lane. Okay, so that's the second probability measure. The third one is simply the probability measure for the observation. So the car follows a certain trajectory. Now this is not conditioned on whether it stays in the lane or not. It may not. So these 3 quantities can be used assuming you have some measures here. And again, these can be very subjective measures, right? But the idea of the Bayesian inference process here is that you use your observations together with these measures to construct a posterior probability, which is the probability that the statement that you're wanting to certify is true given your observation, your measurement of the physical world. Okay, so you take these very subjective measures, you do an experiment, and then you apply the results of that experiment to these measures that you have subjectively constructed, and you come up with a new probability measure that is now informed by your measurements. So the assumption here is that this posterior probability is a better measure of the probability of S because it is informed by experiment. Okay, that's the basic idea of Bayesian inference. And you can iterate this process over and over again. You can take this posterior probability, use it to update your prior, take a new measurement, and then update your posterior again. And you keep iterating this process. And the presumption of Bayesian inference is that as you iterate this process and you take enough measurements, you end up with a very good probability measure for the statement of interest. Does the car stay in the lane? Okay, that's the basic idea of Bayesian inference. Now, what happens when you're certain? So suppose you have written some software to control the car and you apply formal verification and you prove the car stays in the lane. Okay, then your prior probability becomes very simple. Your statement S is simply true. So the prior probability is that P of S is 1. Okay, the probability of any observation given S is just the same then as the probability of the observation. And consequently, these two terms in the numerator and denominator, sorry, let me activate a pointer here. These two terms, this probability, this conditional probability becomes the same as the denominator, and consequently these two terms cancel out and your posterior equals your prior. Okay, so if you're certain about S, you learn nothing from observation. That's the key point of Bayesian inference. Now, you might also have a situation where you're certain that S is false. It's another form of certainty, in which case the probability of S is 0. The probability of an observation is presumably not 0 because you made an experimental observation. It would be silly to have a probability measure that says that can't occur. Okay, so as a consequence, your posterior again is going to equal your prior. It's going to be 0. So according to Bayesian inference, certainty means you can't learn. Observations have no effect on your probability measures. This is bad news for adaptability, right? So it says that really learning becomes impossible once you are certain. Now, that's kind of a trivial mathematical argument for this conflict, right? It says that that we're not going to be able to learn if we're certain about something, and therefore, there's an intrinsic contradiction between this adaptability that we want in terms of intelligent behavior, and the certainty that we want through, formal method proofs of the behavior of a system. But I don't think this is the real reason for the conflict. And so this is where I'd like to give you a much more nuanced and less trivial argument for an intrinsic contradiction between these objectives. So let's have a look at what this AI revolution is really about, right? So the first thing I'd like to point out is that, in the world of certainty, the tools that we use are algorithms, logic, mathematics, rationality. Bundle all those together and you can call that whole approach formal methods. Okay, these are in the realm of the certain. And AI is realized on computers, and computers use algorithms, and algorithms are in this world of the certain. They're formal objects. The computers are just doing symbolic manipulation of formal objects. And so doesn't this put them in the realm of the certain? And I think that the prevailing view in computer science is that, yes, it does, in fact, put them in the realm of the certain. There's a very wonderful quote from the classic introductory book by Abelson and Sussman from 1985, where they talk about the computer revolution, saying it's a revolution in the way we think and the way we express what we think. The essence of this change is the emergence of what might best be called procedural epistemology, the study of the structure of knowledge from an imperative point of view, as opposed to the more declarative point taken by mathematical subjects. So procedural epistemology is knowledge through procedure. So they're kind of equating algorithmic thinking, procedural, with knowledge, certainty, okay, information. They're tying these things together, and they're saying that this is the essence of the computer revolution. So procedural epistemology is all about algorithms. And what is an algorithm? Well, you start with input data, you follow a sequence of steps where each step follows some well-defined rules, and the sequence terminates with a conclusion. Okay? If you limit your data to a discrete set, then algorithms are equivalent to Turing machines. So in the world of mathematical certainty or formal methods, we use proofs. What are proofs? Well, you start with the axioms. You follow a sequence of steps where each step follows well-defined rules, and the sequence terminates with a conclusion. A proof is an algorithm. The rules that are used are typically a little bit different. The starting point is a little bit different, but it's essentially the same structure. Certainty comes from terminating computations or terminating algorithms. That's what leads to certainty in the formal methods world. Now, how do humans apply this? Well, humans do rational thinking. We think through things step-by-step reasoning using clearly explicable rules of logic. We often don't do this, but this is kind of an ideal. But it turns out that humans are actually not very good at this. In fact, Herb Simon got the Nobel Prize in economics essentially for observing this, and he applied the term bounded rationality. And his essential thesis that got him the Nobel Prize was that the prevailing view in economic models at the time was that an agent in an economic system is rational, that the agent optimizes their own personal gain and does so through a rational process. And Herb Simon said, bullshit, and got a Nobel Prize for that. But his essential point was that the optimizations that economists presumed that people were doing were in fact doable through algorithms, but the algorithms were intractable to humans. The number of steps was too much, the amount of data involved was too much, and so humans were actually not able to be rational agents in these economic systems because we don't have the capacity to do that level of rational process. Now, many of these optimizations are in fact accessible to computers. And so computers could be rational agents in an economic system, but not humans. Now, let's look at the second computer revolution, which is the one that we're really in the middle of right now, right? The emergence of the LLMs and the revealing of the incredible power of these deep neural networks. So my question here is, are these foundation models usefully understood as rational machines? My claim, these new machines are not about procedural epistemology. They're changing the game completely. We have entered a second computer revolution that is really quite different from the one that Abelson and Sussman identified in their introduction. Procedural epistemology is not at the root of what these machines are doing. So one way to see this is that, we can put the tools of rationality side by side with sort of their counterparts in an intelligent system. So logical reasoning versus intuitive reasoning, right? I mean, Herb Simon's point was that intuitive reasoning is a very big part of how a human agent behaves in an economic system rather than logical, okay? Reasoned versus creative, dispassionate versus emotional, predictable versus adaptive. Are we really looking at certain versus intelligent here? That's the question that I'm asking. Now, one of the interesting things is that there's a lot of people still, since 2022, with the first emergence of ChatGPT, with every new release of an LLM, there's critics who jump all over it and try to debunk it, right? To say this is all hype. The machines are really incapable of doing stuff that they should be able to do. So one example, I mean, I won't name the blogger, but a very prominent blogger on this and a frequent critic of the AI hype. When GPT-4 came out, he did a test. He asked GPT-4 to construct a table of the 50 states in the United States, the capital cities, and the population in the capital cities. And the LLM happily responded with a table that was full of errors. And he said, you see, it's not as smart as you think it is. It's all hype. This blogger was expecting the machine to behave like a computer, but it didn't. It behaved like a human. I mean, try asking a human the same question, and you're going to get an answer full of errors, or perhaps more likely an answer like, what a ridiculous question. The question that he should have asked GPT-4 is to construct a SQL query to query a database to construct the table. And that GPT-4 would have done flawlessly. Okay, that kind of thing it is really good at. So in essence, he was asking the LLM to do what computers have done since the 1950s, which is process a bunch of data and construct tables. But what the machine is doing is really much more interesting than that, and really quite different. So how is it different? Well, I think it's actually lying more on the right-hand side of this equation, of these counterparts rather, than it is on the left-hand side. And yet people are expecting it to be on the left-hand side because it's a computer, okay? So they criticize the machines because they make stuff up. They give you answers that are invented. Well, is that hallucination or is it creativity? So here are some images generated by AIs quite early in the LLM revolution. So these are both, this is from 2022, this is from 2023. These are images that won grand prizes in art competitions, juried by art experts. Is the right term hallucination here? Or have we actually identified perhaps a foundational mechanism behind the concept of creativity? Is there something that we could learn about human creativity from the truly remarkable fact that these machines are suddenly able to do things that we never expected computers to do? Another criticism that's very common is that, they're just stochastic parrots, right? They're just reflecting what's in the training data. you can do a simple, very simple numerical calculation that shows that really this can't possibly be the case from just an information theoretic perspective, right? The amount of data in the parameters of an LLM model is so much, or many orders of magnitude smaller than the amount of data in the training data set. And so they can't have memorized more than a small fraction. You know, perhaps the machines will have memorized some of the more famous quotations from Shakespeare, for example, because those have appeared so many times in the training data set. Same as humans, right? I mean, how much of your training data can you parrot, right? I'm sure you read many classic books when you were young in high school. Can you remember what those books said? I don't think so, but they had an influence on your training, okay? And the same is true of these LLMs. So, you know, if you want to verify that they're not stochastic parrots, just ask them weird questions like this one. You know, please express the following sentiment in the style of a parrot. Today's large of a pirate. Sorry, not a parrot. Today's large language model AIs are merely repeating content they have harvested from the internet, and they're therefore plagiarizing material written by humans. So here's the answer I got from ChatGPT, and this was GPT-3, okay? Ahoy there, me hearties. Listen up, ye scurvy dogs. These fancy newfangled large language model AIs be naught but mere parrots squawking the same old content they've swiped from the interwebs. They be nothing but thieving scallywags, plagiarizing what us humans have worked so hard to write. Aye, 'tis a sad day when the machines be stealing our hard-earned words. Arg. This is not a stochastic parrot. This is really pretty remarkable reaction from the machine. And this is just the early stage. And sure, they make mistakes. So, you know, one other blogger criticized ChatGPT, no, the Google search, sorry, when they first started integrating the AI. And, you know, I asked Google, can you melt eggs? Yes, an egg can be melted. So I asked ChatGPT to create an image of melting eggs and got this pretty remarkable image. They make mistakes, indeed. That's more like humans than like computers, right? And yet people are expecting them to behave like computers. Now, there's this wonderful paper that was published more than 2 years ago, but it's still the best read I've found if you really want to get insight into what this transformation really means. This paper is over 100 pages. It's available on arXiv, and it has a very detailed study doing a comparison between GPT-3 and GPT-4. And it has a whole suite of problem areas that it does this evaluation. And it has a tremendous amount of insights into how these machines are really different from the classical rational computations that we're used to from computers that we've been using for decades. Okay, so I'll just pick a couple of examples from the section of the paper that is looking at algebra problems. And there's, you know, a whole suite of kind of problem areas that are addressed in this paper, but algebra problems are ones that I kind of resonate with. And so it, you know, has some interesting insights. So in particular, here it gives an algebraic expression and asks GPT-4 to simplify it, and GPT-4 comes up with an answer that's just wrong. So I want to emphasize that there's no use of symbolic algebra tools, right? We've had, you know, computers have been able to simplify these expressions for decades now, you know, since at least the 1990s when we got very sophisticated symbolic algebra programs. GPT-4 was not using any symbolic algebra program, right? This is just using the token prediction that is underlying the model. It's truly remarkable that it would be able to accomplish anything with just token prediction on a problem like this, in my view. But a much more interesting insight in this paper is that they then asked GPT-4 the same question, but said, simplify the equation, try to move each term step by step. Okay. And GPT-4 then went through a sequence of steps and actually came up with a correct answer. This has since become routine. In fact, DeepSeek was, part of the DeepSeek revolution was to integrate chain of thought reasoning into the essential mechanism by which the model would produce a response. It would always do this chain of thought reasoning, and as a consequence, a smaller, simpler model could give better answers. Interestingly, this also works with humans. Every teacher in high school knows that if you get your students to give you step-by-step answers, they're going to give you better answers than if you don't ask them to show their work. Okay, this is a standard teaching practice for humans. Humans do better if you actually break it down into smaller steps. So this chain of thought prompting has become part of the bread and butter of the large language models. The coding models that are particularly tuned to writing software do this tremendously detailed ways, and it dramatically improves the results. Okay, let's look at another problem that's in this Bubek et al. By the way, the authors of this paper are from Microsoft, and so this study was done at the time that Microsoft was evaluating whether or not to invest heavily in OpenAI, and I think partly as a result of this study, they plowed very quickly some $10 billion into OpenAI, and so I think that's another good reason to look at this paper, is that in a sense it really was a very systematic study of a potential investment. Okay, so in the paper, it gives a word problem. This is the kind of word problem you would typically find maybe on an SAT, college entrance exam or something like that. So it says, within the duration of 1 year, rabbit population first multiplies itself by a factor of A, and on the last day of the year, B rabbits are taken by humans for adoption. Supposing on the first day of the first year there are X rabbits, we know that exactly 3 years afterwards there will be a population of 27X minus 26 rabbits. What are the values of A and B? Phew. Well, this looks like a colossal chore to me. I mean, I doesn't look like fun to solve this, but give this to the AIs and they give you an answer. And so ChatGPT, which was GPT-3 at the time, gave an answer that was all wrong. But if you look at it, if you were teaching high school, you'd give partial credit for this. There was some reasoning going on. Okay. GPT-4 got the right answer, but made a kind of interesting implicit assumption about an equation that it just assumed it had a solution without really verifying that. But so this paper actually prompted me and a colleague from Tunisia, actually, Moez Ben Hajmida, to do a bit more detailed study and look at the kinds of mistakes that were made in 3 different generations of LLMs. And we started with GPT-2 because it was part of the history, and it was a model that we could run on our laptops, and so it enabled us to do a bunch more experiments than we could afford to do with the online models. But we sort of classified the mistakes that came along, and the mistakes looked remarkably human, but like GPT-2 would make really silly mistakes that, you know, a kid might make. They were sometimes really funny, and you know, kind of cute, right? GPT-3, you know, maybe a 15-year-old. GPT-4, you know, more like our Berkeley grad students. It was really pretty remarkable. I mean, sometimes they would make mistakes and we would not recognize it as a mistake immediately, and would really, before we realize, oh my goodness, that answer is wrong for a very subtle reason. Okay. So, you know, what is going on in this machine? It's just doing token prediction, right? But here's a follow-up question that Bubek and his colleagues asked the AI. They said, you know, note that the above question can be alternatively formulated as a question about a function which is composed with itself 3 times. Can you provide an alternative formulation of the question? GPT-4, yes, we could say that we're looking for the values of A and B such that blah. This blew my mind when I saw this in this paper. This is not a stochastic parrot, okay? This didn't read this in some problem in the training data set. The machine is reasoning about symbolic algebra in much the way that a human would reason about symbolic algebra. And it's doing so incredibly quickly. And yes, it makes some mistakes, but it also gives some very definitively correct answers. How on earth did this come about from just predicting tokens? The computer is not doing algorithmic thinking. The chain of thought mechanism is a way to kind of prompt it to do algorithmic thinking, but it's doing it, even with the chain of thought reasoning, it's doing it more in the Herb Simon sort of bounded rationality kind of way. It's using a very limited number of steps, and each step is actually not itself algorithmic thinking. It's much more like intuitive thinking, okay? So the concept of numbers does not rely on the arithmetic hardware in the machines. It's not using symbolic algebra system. It's just predicting tokens. To me, this is the most amazing thing about this large language model revolution. And I think it teaches us a tremendous amount about very likely how the human brain works with its own rationality. So from token prediction, we get these emergent properties, an ability to reason and use logic in limited ways, bounded rationality still, perhaps less bounded than with humans, but still bounded. The ability to do arithmetic without using arithmetic hardware. The ability to do math without using symbolic algebra programs. The ability to write computer programs. And yes, these days you do get them to do chain of thought reasoning. So when they write a piece of code, they also check it with the compiler for syntax correctness. The ability to be creative and produce things that look like artworks to us. So these things I used to think were the foundations of intelligence. And it looks like they're not. It looks like they're emergent properties. They emerge from intelligence rather than being the foundations of intelligence. So after publishing this paper, Bubek gave a TED talk on it. And in this TED talk, he really summarized rather nicely. The truth is, nobody has a clue what's going on. These are the world's top experts in AI. All of them were blown away by what these models were able to do. Okay. So let's go back to the question now of certainty versus intelligence, right? You know, maybe we can get certainty through explanation, right? So we'll integrate the AIs into our system, but we want explainable answers. There's a lot of very nice work that's been going on that gets us steps closer to this. But there's a very big red flag that I'd like to raise about this approach, right? So let's look at what is an explanation? Well, you want to answer the question, why? Why is this answer the right answer, right? Well, one view of an explanation is that you start with the input data, you give a sequence of logical deductions where each deduction conforms with the rules of logic and the sequence terminates with a conclusion, okay? If you give this explanation for why did the LLM come up with this answer, if you give it in terms of what the computer is actually doing, billions, trillions, quadrillions of arithmetic operations, that's not going to be a useful explanation. It actually does follow this sequence. It is ultimately algorithms that are doing this, but a description of those algorithms does not constitute a useful explanation. Okay? So if you want an explanation that is accessible to a human, it's going to have to conform with this bounded rationality that we have, which means we can only really handle a few steps with very limited data. And consequently, the explanation is going to have to be a very short algorithm, not what the computer is actually doing. So what does this say about, some of the attempts to regulate AI? Well, one of the things people keep calling for is algorithmic transparency. Show us your code. But I've looked at the code and it doesn't help. Knowing the operations that are done by the computer does not help a human determine whether an output is justified. It really doesn't help. So that's, I think that there are people who naively expect to find, somewhere in the code, there's a hidden statement that if the applicant for a loan is female, the loan should be denied. Well, there's no such if statement in the code, and you're not going to find it through algorithmic transparency. If there is such a bias in the code, it's going to be a bias that derives from the training data, and it's going to be very difficult to find and explain that bias. What about the right to an explanation, right? This is built into, there's a clause in the GDPR and certain other rules in European laws that give a right to an explanation, but if the explanation is given in terms of what the computer actually does, it's not going to be a useful explanation. So what kind of an explanation might be a useful explanation? Well, there's this wonderful work about humans by Daniel Kahneman, another Nobel Prize winner, that is very nicely written in this book, Thinking Fast and Slow. And Kahneman identifies two very different kinds of decision-making that humans do. He called them system 1 and system 2. And system 1 is intuitive, quick, inexplicable decision-making. It's the decision-making that you use all the time when you're looking at a menu in a restaurant and you decide okay, I'll order that, right? You didn't go through a sequence of rational process. Well, maybe you tried, right? This has lower fat than that, so maybe I should order that one. But ultimately, your decision-making is probably dominated by system 1. System 2 is the rational decision-making, and according to Herb Simon, it's of the two, we're much better at system 1 than system 2. And it's only when system 2 dominates does the true origin of a decision correspond to a rational explanation. If it's a system 1 decision, then if we can give a rational explanation, according to Kahneman, it's a post hoc rationalization. In other words, it's a rational explanation for a decision that is constructed after the decision has been made. So the rational explanation is not how the decision came about. It's a rationalization of how the decision came about. The way the decision came about was system 1, and really ultimately was inexplicable. So My claim is that deep neural networks are much more like system 1 than system 2. It is not useful to think of them as doing rational decision making. That's not what they're doing. So the difference between an algorithm and an explanation, well, according to this model, an explanation is an algorithm. It just has to be a really short algorithm. So going back to this juxtaposition, the rationality on the left, intelligence on the right, right? The claim here is that the left-hand side is limited by the principle of bounded rationality. Interestingly enough, today, it's even limited in the LLMs as well, right? Their chain of thought reasoning breaks down at certain points, but it works very well if you keep the number of steps reasonably short, okay? Similar to humans. So certainty or intelligence, well, it seems like the left-hand side is this world of formal methods. And the hope was, I think, that we could deal with this with the LLMs simply because they are ultimately implemented by algorithms on computers. But I think there's a fundamental contradiction here, and I'm pretty certain about this. Now, okay, so we've got a contradiction, but I'm an engineer. So it's not uncommon in engineering to have contradictory goals, and you got to deal with it. So what are the tools that we have to deal with it? Well, there's a few things we can do, right? One is treat the AI component in a system as part of your sensor system, okay? This works for perception. So in other words, one way to think of a system is, you've got sensors giving you data, and then you think of your system as being, an AI deciding on a plan, and then your control law implementing the driving the actuators. And you might think of trying to verify this compute box that includes the AI. You're going to have a lot of trouble doing that, according to this principle. But you could refactor this system and simply think of the AI as part of your sensor. So your sensor is feeding a perception engine, which is giving you potentially flawed data. So engineers are used to dealing with noisy sensors. So it's not a new thing to have to deal with noisy sensors. So for certain kinds of applications of AI, this might be a perfectly reasonable way to refactor a system. And then you apply your verification to the control law, not to the AI. A second technique that could be used is what is called in the avionics world envelope protection, which is simply that you limit the actions that an AI can take. So in other words, you do include the AI in your compute system, but you don't take its raw output. You instead apply envelope protection. So in avionics, this has been done for decades primarily by Airbus. There's been an interesting sort of philosophical debate between the Europeans and the Americans on this. And Boeing, for the most part, has refused to put flight envelope protection into their control systems in the plane. They say that, if a pilot wants to put a plane into a stall, the pilot should be able to put the plane into a stall. Whereas the Airbus control systems will prevent the pilot from putting the plane into a stall and will ignore the actions of the pilot up to a certain point in order to prevent the plane from going into a stall. So flight envelope protection is about limiting the actions that humans can take, human pilots. But you could apply the same principle to AIs. Treat them like humans, don't trust their output, and restrict the actions they can take. That's another engineering approach that's available to us. A third approach is to try to achieve algorithmic confidence. So rely on formal methods, theorem provers, model checking, for example. There's been a lot of work on trying to apply this to AI, and some successes. There are some successes, but they're very limited. They're limited to small systems designed with the help of machine learning. I have not seen any successful applications to machines that learn. Okay, only to machines that were designed with the help of learning. And I think formal methods are not really showing promise of scaling to the magnitude of the computations involved in these AIs. So I'm really honestly not very optimistic about this approach. So in summary, certainty or intelligence, contradictory goals. What I've said, certainty prevents adaptability. Trivial argument is Bayes' law. Certainty arises from rational processes. Bounded rationality limits this. Formal methods are not going to be able to scale to deal with how the AIs are actually implemented. Intelligence requires adaptability, and consequently, we may have to relax our requirements for certainty. So the more profound observation is that it seems that intelligence is rooted in prediction, not rationality. It appears that rationality is actually an emergent property from intelligence rather than its foundation. So here's a few citations. These are all open access. And even though these two books were published before the LLM revolution, they actually both have had, I think, remarkable staying power. And there's a lot of insights about the underlying mechanisms that I think I still stand by, even though the world has changed since I published those books. Perhaps the most relevant to this particular talk is the only paper I've ever published in a psychology journal, which is entitled, "What Can Deep Neural Networks Teach Us About Embodied Bounded Rationality?" And that paper goes into much more technical detail about these arguments. So I'll stop there and take questions. Thank you.
Thank you so much for this very inspiring talk, Edward. Really enjoyed that one. So let's open the floor for questions. So raise your hand or just speak up if you have a question. Who can I give the floor for questions? Don't be shy. So in the meantime, let me start with asking a question. So what are the implications of all of this to, let's say, all the efforts, especially in industry, to achieve fully autonomous systems like autonomous driving and things like that? Are they doing the wrong thing at this moment in your view? Should they really change the way how they are trying to achieve this, or what's your view on this?
I think that one important implication is that that we may not be able to apply the techniques that have been quite successful in creating very safe engineered systems like aircraft, right?
Right.
A spectacular track record of making technology that is very safe, very predictable, remarkably safe, remarkably predictable. These methods, I don't think, are going to work in this context. And I think one consequence of that is that when we're vetting technologies to decide how much authority to give them, how much autonomy to give them, can we put them in public spaces, things like that, we have to vet them in the way that is much more similar to the way we vet humans. So, how do we vet human drivers? Well, we have a driver's license scheme. We require them to take certain driving courses. We have a driving test that checks to see whether they are, able to do certain basic functions. We may have to really elaborate these tests for the AIs, but it may well be that our vetting processes are going to have to be like that. They're going to more closely resemble the way we vet humans. We want, to have autonomous systems making decisions about bank loans and so on. Well, how do we vet humans to make such decisions? Well, we have, performance evaluation processes, promotion processes. People start out in a low position in a bank. They slowly work up and they are slowly given more authority. They sometimes make mistakes. They'll get demoted. They get fired. It may be that that's what we're going to do with AIs. We're going to demote them and fire them when they make mistakes.
This must be a major disappointment for some people who are dreaming about fully autonomous systems and getting rid of all those things that we have to use for humans. And now what you're saying is we will not get rid of those things.
Right.
Yeah. Very interesting. Yeah, very interesting. Okay, so other questions? Job, you have a question.
Yeah, I had a brief one regarding your change in approach to seeing the AI as part of the sensor. How does that influence a system that is already noisy? Like, since your AI is not explainable on its own, like what does that do to actually determining what's noise and what is valid?
Yeah, that's a very good question, and I think that there's a lot of problems with this approach. I mean, one is that I should point out immediately is that people who are working on self-driving cars have realized that this approach actually is not a very good approach, right? If you put the AI in the sensor system, then you try to do things like have it produce an output that identifies whether there's a stop sign at this intersection. And people find that these systems are really quite brittle and can be fooled. And so they're, practitioners in the field are finding that end-to-end systems are more effective, where the AI isn't part of the sensor system, but it becomes the whole control system. Okay. And that those are actually harder to fool. They're more tolerant of noise in the sensors than when you put the AI as part of the sensor system. So that approach has its problems, has its limitations. And I think, the circumstances, I think that in the self-driving car world, it's been shown pretty definitively that you don't want to use it to create a sensor that detects road signs. That's not going to be a good use of this technology. On the other hand, I think that detecting lane boundaries has actually proved pretty effective using these techniques, right? So, lane boundaries are kind of hard to detect. I mean, anybody who's driven in Boston on a rainy day knows that sometimes you have no idea where the lanes are, right?
It's not only in Boston, I can tell you.
And so, lane keeping systems have to be able to deal with that kind of situation. And I think that, in that particular example, my impression from people I talk to in this field is that they have found that an AI can be pretty useful if viewed as part of the sensor system. But don't try to use them to detect stop signs. That's in a sense too high a level piece of functionality, and it's factoring the system at the wrong boundary.
Awesome. Thank you.
So apparently there is maybe a problem with raising hands. So if you have a question, just raise your voice. Is there anyone who has a question? Just raise your voice.
Just a sec. I think only cameras are allowed. I'll also turn on the voice if needed.
Any questions?
Yeah,
Are you
microphones should be able to be opened if you want to.
I hear nothing. So no questions from the audience.
Well, maybe this is a good time to end.
Yeah, I think so too. So let me thank you again for this wonderful talk, Edward. So I really enjoyed it. Hopefully the audience as well. So again, thank you so much, and also for getting up so early in order to give this talk. And I hope to see you. Are you going to ES Week this year?
Yeah, I'll be there.
Okay, then I'll see you over there. So that's great to see you again in
Okay,
person.
on the other side of the world for both of us.
Exactly. Okay, so thank you everyone for attending. And then with this, we end this wonderful talk of today. So thank you again.
Thank you, Lee.
And see you. Bye-bye.
Bye.
Bye.